As I told you earlier, this section has been divided into two parts. In part one, we talk about the critical points and increasing and decreasing interval for the given function. And in this part, we focus our attention on the concavity. And at the same time, we'll also discuss second order derivative and higher order derivative. So what does that second derivative and higher order derivative? Let us take one simple example, okay? Let us talk about this and then we come back to the concavity. So what is higher order derivative? Let us suppose that f of x is given, let's say x power 4 plus 3x square minus 2x plus 1, for example. If I ask you find that first derivative, then your answer would be 4x cubed plus 6x minus 2. Not a big deal. If I ask you to find the derivative again, you will come up with 12x squared plus 6. Not a big deal. If I ask you find the derivative again, then you will say it is 24x plus 0, so simply 24x. If I ask you find the derivative again, how many? 4. Okay, 1, 2, 3, 4, and then that's going to be 24. If I ask you to find the derivative again, 1, 2, 3, 4, 5, and it will be 0. In the same manner, if I ask you to find the derivative of 100th derivative, for example, then you will come up with 1, 2, 3, 4, 5, 6. Oh, that's too much. That's too much to write, okay? And so we don't want that. If I ask you find the 1000th derivative, then do you want to draw those 1000 lines? No, right? We don't have time to just draw that thousands lines. Okay, I know you guys are busy, so I don't want you to do that. So what we do now is that we just write 100th this way to make life easy, okay? So even this 5, right, drawing the line, drawing this 5 lines, that's too much. We simply write 5 there. This 4, again, it's too much for me. But if you want, you can draw those, you can just write those lines. That's okay. But my concern is that it's too much tedious. Okay, up to 2, then let's do, let's use the prime, and after that, let's use this number so that we can save time. Okay, this is all higher order derivative. This is your first order derivative. This is your second derivative, third derivative, fourth derivative, and so on. Notice how I denote the third order derivative like this way. It's not like f of 3, not like that. This 3 is on the top of f, okay? In the same manner. F is on the top of F, like that. All right, now with this concept, I would like you to try this example 3 on your own. So let's look at example 3. What is there? Find the second derivative of the function. Okay, we need to find only second derivative at the specified value of x. So part A, f of x is this. Now you want to find the derivative, which is f prime of x, which is 20x cubed minus 12x squared plus 3. That is your first derivative. Now your second derivative is going to be 60x squared minus 24x. And now we need to find what is the value at x equals 1. So you just find at x equals 1, that's going to give me 60 times 1 squared minus 24. And I think you know the answer, which is 36. Done. Okay. In the same way, I want you to try part B just for fun. Okay. Part B. Let me write that part B somewhere here. Okay. I don't have a space there. Let's do part B here. g of x equals x e to the x. I just copied the question. Now you know that we need to use the product rule, u times v, and the derivative is going to be uv plus uv prime prime. So that's going to give me u prime, which means derivative of x, which is 1 times e to the x, plus v, which is, u, which is x, and then derivative of b, which is derivative of e to the x, is e to the x by itself. So it is e to the x plus x e to the x. So that's our first derivative. Now for second derivative, our second derivative is going to be, see here, this one, derivative of that is going to be itself. Okay, second derivative, what we need to do is we need to find the derivative of this, derivative of that. So derivative of the first term will be e to the x by itself, and derivative of the second term we already calculated. So derivative of e to the ex is we already calculated, which is e to the x plus x e to the x. So if you combine them, your answer is going to be 2 e to the x plus x e to the x. Now we need to find second derivative at the value, when x equal to 0, that is going to be 2 e to the 0 plus 0 times e to the 0. So this will be 2 e to the 0 is 1. You already know that. Plus this guy is 0 in the second term. That's going to give me 2. Okay? It's that simple. So can I trust you that you will be able to do this part C, part C right here by using the, quotient rule? Okay, I'll trust. I trust that you will be able to do it. Now, so second order and higher order derivative, I think you know what it means. Now we define the concavity. Let's go back all the way here. Now, another very important concept that we'll be talking about is concavity. As you saw earlier at the beginning of the class, in part 1, so concave up means something like this. It is concave up. As you can see here, this part is concave up. This is concave up, and this is concave down. Now, the interesting relationship between this concavity and the derivative is that concave up means the second derivative is positive. Concave down means the second derivative is negative. Okay, so if we want to talk in the language of calculus, we say that the second derivative is positive for concave up. Okay, if people say, okay, that is concave up, so you can say that, oh, second derivative is positive. Concave down, oh, that second derivative is negative. Now the question is, what happens when second derivative is not positive, not negative, means there are only two possibilities. When second derivative is 0 or second derivative is undefined, then what happens at that point? Well, let's look at this here, this graph. As you can see, all the way from here all the way up to this point right here, let's say this is my C, this is A, this is B, this is C. Now, as you can see here, this graph is concave down from negative infinity to concave down from negative infinity to C, and concave up from C to infinity. Okay, now that means concave down this side means your second derivative is negative because it is down, negative. Okay, you see, down means negative. You can think this way. And up means, right? negative here and positive there. And this side is concave upward, that means second derivative is positive. At this point, we call it inflection point. So in short, I call it IP from now onwards, okay? When I say IP, then I'm talking about inflection points. So inflection point means the second derivative is either 0 or undefined. In this case, it is 0, but sometimes it will be undefined as well. Okay, so remember, if you compare this with the previous concept, so for critical number or critical point, your first derivative equal to 0 or undefined. For inflection point, your second derivative is 0 or undefined, same thing. In the previous case, increasing function means your first derivative positive. Now concave up means second derivative positive. Decreasing, function decreasing means first derivative negative. Concave down means second derivative negative. Every step is exactly the same as we did earlier. So let's try example 4. In example 4, we need to find all inflection points and the interval where the function is concave upward or concave downward. Okay, in this example, we need to find inflection point, and you need to memorize this, guys. Inflection point occurs when the second derivative is 0 or undefined. Okay, in the same manner as we talk in the previous lecture, in the previous part 1. Same thing. Now, in order to do this example 4, let me just copy this question 4a. We'll do 4a together, and part B you'll do by yourself, okay? 4a. So let me just copy the question. Okay, question number 4a. The question is f of x equals x cubed minus 6x squared plus 12x plus 5. Sorry, minus 5. This is my question. Now, step 1, find the first and second derivative. Your first derivative is going to be 3x squared. Okay, guys, let's do it together. Find the first and second derivative. 3x squared minus 12x plus 12. And then find the second derivative, which is 6x minus 12. Now, step 1, for critical number, not critical, here we need to find inflection point, sorry. For inflection point, so from now onwards, I call it IP. We know that inflection point occurs when the derivative is 0, second derivative is 0, or second derivative is undefined. We know this. And you see the second derivative is 6x minus 12. It is not a rational function. Therefore, there is no way that you can make this function undefined, because for undefined, it has to be something like, if we have this kind of function, then in order to make this undefined, the denominator denominator must be 0. But in this case, there is no way that you can make the denominator 0. Therefore, no such point. Okay, the second derivative is never going to be undefined. Now, second derivative we can make it 0 by supposing this. equal to 0, which means x equals to 2. So now your inflection point is x equals to 2. Okay, that's the x value. But if you want to calculate what is your y value, you can calculate that as well. Suppose you want to find y. If you want to find y means the function f of 2, which is 2 cube minus 6, 2 square plus 12 times 2 minus 5, and that is going to be, I believe, 3. So your IP is 2 and 3. So here, sometimes you may want to find the y value, but what is important is the x value here, okay? Because now step 2 is we are going to draw the number line exactly the same way as we did before. Let us draw the number line to find the interval for concavity of the function of f of x. Okay, for this, what you do is you consider the number line. Okay, consider the number line exactly the same way as you did before, and plot that x value here. And so this IP divides the number line into 2 intervals. Now consider the testing point. So testing point, you can choose any value between negative infinity and 2. So you can choose, minus 37,246.36. You can choose minus 50.78, whatever. But my suggestion is try to make your life easy. I think the easiest one would be if I suppose x equal to 0. That is the easiest number to calculate. So I suppose x equal to 0, and I need one number from the second interval. So second interval means any number between 2 and infinity. So let me choose 3. I think that is the easiest number. Now all we need to do is test these numbers in the second derivative. Let me just copy the second derivative here. So the second derivative is 6x minus 12. So if I put this 0 testing number, okay, let us test that. If I put second, x equal to 0, that's going to be negative. So that means this side is negative. The sign is negative. What does that mean is when the second derivative is negative, we know that it is concave down. Let me just make a, sign for concave down like this. And then your second derivative, when x equals to 3, what happens? When x equals to 3, this is going to be 6 times 3 minus 12, which is positive. So this side, it is positive. So the shape of the graph is like, concave up. So we already got all the answers here. So what we got is, your answer is, your IP is, inflection point is 2 and 3. F of x is concave up. On the interval, concave up on the interval 2 to infinity, and concave down on the interval negative infinity to 2. That's it. Okay, this is the main thing for this section, guys, for this part. If you have any question, let me know. Otherwise, you may want to try one questions on your own, just for fun. Part B. Okay, guys, big warning. What we have noticed and what we have discussed is that inflection point occurs where the second derivative is 0 or second derivative is undefined. That's what we said. Now the question is, here is a big warning. Note that it is not enough for the second derivative to be 0 or undefined. This is not the sufficient condition, okay? In order for this to be IP, the second derivative must be 0, and these are the only possible location for IP, okay? These are the possible location for IP, but they do not guarantee that the IP actually exists. Let me repeat this. Second derivative equal to 0 and second derivative undefined, these are the possible points where IP occurs, where inflection point exists. But it is not sufficient. If second derivative is 0, does not necessarily mean that this is IP. In order for this IP, then this must be 0 or undefined. In the same time, on one side, the concavity must change. Like this, the concavity must change here. So here, it must change. It's concave down and then concave up. So one side must be positive, another side must be negative. Now let us look at one example, what I mean. Example 5. I draw the graph for each of these functions. We have three functions here, f, g, and h. F of x is x cubed, g of x is x to the power 4, and s of x is x to the power 1/3. All right, and I have drawn the graph. I trust that you will be able to draw the graph. And actually, I use this geozebra.org to draw the graph, but you can use any online platform, okay? Online software. There are so many online software available which you can use. And if I draw the graph of f of x to the x cubed, then notice that this side is concave down all the way from here. So it looks like this side is concave down, which means second derivative is negative. And this side is concave up from that point. So the second derivative is positive. Therefore, this is my inflection point. Now, I want you to let me know what is the inflection point for this second graph and third graph. Take few seconds and then let me know what are the IP, second and third. Now, let us look at this by the method that we saw earlier, okay? S of x equals x to the 1/3. Now, f of x is x cubed. Your first derivative is 3x squared, and your second derivative is 6x. So we know that for IP, you have second derivative equal to 0 or undefined. So that gives me 6x equals to 0, x equal to 0. In second figure, g of x, so your g prime of x equals 4x cubed, and g second derivative is 12x squared. So by definition, your IP, if there is any, must exist at where the second derivative is 0. So that gives me 12x squared equal to 0, which means x equal to 0. Now, when x equal to 0, y is definitely 0, you know that. So y means f of 0 equal to 0. Here also y equals f of 0 equal to 0. Now, for the first one, now let us look at what happens. If 0 is here, okay, and now you have negative infinity to infinity testing point. For the first one, your testing point would be, let's say, -1, and the second testing point would be 1. So your second derivative is 6x, and your second derivative, when you put that -1 there, so you're going to get -1, which is negative. So this side is negative, means concave down. Now your f, when you plug in this x there, you're going to get 6 times 1, which is positive. Positive means concave up. Since the concavity changes, okay, as you can see, the concavity changes, therefore x equal to 0 and y equal to 0 is IP, inflection point. Now in the second case, let us look at the second z function here. What happens? For z function, let me go here to there. If I draw, you know that we thought that the possible IP is 0, so there is 0 and we have negative infinity to infinity. Testing point will be, testing point is again x equals to -1 and 1. Now let me just copy that h here. Oh, not h, g, sorry. G prime of x is 12x squared. So g prime of x, if I put that -1 there, I'm going to get 12 -1 squared, which is positive. And this is positive, which means concave up. So the second derivative is when I plug in x equal to 1, I'm going to get 12 1 squared, which is also positive. Also positive. So no sign change. No sign change. So no IP. Okay, so make sure that in order for this to be IP, the sign must change. In another word, the concavity must change. And we have seen that in the figure. So in this figure, yes, this is IP, but here no IP. In the same way, you can think this one. No issue there. Any question, guys, so far? Okay, let's do the last problem from this section, which is example 6. It is the application of inflection point in the real world situation, particularly in economics. Okay, by the way, in the language of calculus, we call that point, this kind of point, as inflection point. But people in economics, in the language of economics, they call it point of diminishing return. Have you heard this word before? I think if you have taken economics course, I think you have heard that, okay? Point of diminishing return. Here. Can you see that? Point of diminishing return. So that is the word they use in economics, but in mathematics, in calculus, we call it inflection point. They mean the same thing, by the way. All right, so example 6, we are given the function, a revenue function. Guys, I want you to try this on your own, okay? I trust that you'll be able to do it. So let me just copy that question. So the revenue function is given 600x squared minus x cubed. What we want to do is the interval is given, the domain is given, x lies between 0 and 500, where r of x represent the revenue and x represent the amount spent on advertising. Find the point of diminishing return for the function r of x. So that means you just find the inflection point. So find the first derivative. I trust that you know how to find it. Find the second derivative. I trust that you know how to find it. And then for inflection point, your r prime of x equal to 0 or undefined. Undefined. So There is no such number. Now this side, okay, let me know what is this second derivative is. So the first derivative is this, and the second derivative, you can calculate this by yourself, which is going to be 1 over 50,000 and 1200 minus 6x. So IP is the second derivative equal to 0, so that's going to give me 1 over 50,000, 1200 minus 6x equal to 0. So this gives me 1200 minus 6x equal to 0, gives me x equals to 200. Okay. All right, so we found that it is x equals to 200 is the inflection point. Now, in order to check whether this is inflection point or not, what you need to do is you need to check the interval, whether, left side, right side, if it is positive, negative, what happens, okay? So check. When x is 200, you draw a number line, negative infinity to infinity. This is your 200. Now testing point, x equals, on this side, maybe your testing point would be the easy number to deal with is 0. And it's 0 in the domain. I think the domain is 0, including 0 to 500. Okay, x equal to 0. And then another point on this side, you may choose 300 maybe. So your second derivative of x, let me just copy that, which is 1 over 50,000, 1200x minus, not 1200, 1200 minus 6x. So this is my second derivative. If I plug in x equal to 0, I'm gonna get 1 over 50,000, 1200 minus 0, that's gonna give me positive. So this side is positive, and this means concave up. Now your second derivative, when you plug in 300, what happens? 1 over 50,000, 1200 minus 6 times 300. Clearly this is negative because this 6 times 300 is 1800, right? So negative 1800 and 1200. So that is clearly negative. So this is negative, concave down. So yes, so IP exists at x equals to 200. So your IP is x equals to 200, and then you can find y, which means r of 200. You plug in the original function. You see y means the original function, which is 1 over 50,000, and then you'll have 1200. Okay, what is that function? This is, okay, 1 over 50,000, 600 x means 200 square minus x cube means 200 power 3. And then if you simplify it, you're gonna get, okay, I'll wait. Okay, this is 320. Then your IP is, IP means your inflection point, which means diminishing return. Hence, your point of diminishing return is 200 and 320 done. That's it.